My name is Diago, and I'm from Meiji University, and I will continue the presentation I did in the last time meeting. So at that time we were preparing some patent, so could not explain in detail what we did related with the Kirigami Honeycomb. So in this time we will explain how we use the Kirigami Honeycomb and focusing on the continuous manufacturing method. So I will go to the approach we use and show some preliminary results, conclusion, and future works. Uh, from the Kirigami Honeycomb related with metamaterials, so there are several approaches for the metamaterial development based on Kirigami. So in the previous, for example, in the Tachi presentation, Professor Tachi presentation, he shows some approach for the Kirigami for metamaterials. In our case, we focus on the Kirigami based on the honeycomb approach. So for the honeycomb approach for the metamaterial, there is some work developed in Bristol University by Neville Cho and this group in Bristol University, where they show that for the honeycomb, the angle theta and the angle alpha in the picture can be changed, and according to these two angles we can know the properties according to our aesthetic different materials. So the green part in the front part is related with our aesthetic behavior, which was shown also by Professor Tachi, where you apply some force in some direction and the shape of the material will change uniform in all direction instead of a non-aesthetic material. So in this case, we almost all the works developed by the focusing on the Kirigami honeycomb are based on the initial approach proposed by Nojima and Saito and Professor Saito when they proposed to develop some uniform to the honeycomb based on two curved uniform honeycomb, and they find some equation to transform from the 3D case to the 2D by including some slant in the pattern. So after that, and they show that this can be manufacturing in a continuous line. So in this case, Nojima and Saito then they use two curves. I mean the T curves in the top side, using some points to develop some curve in this cross section, and also in the lower part. And from these two equations, they can define different shapes of the slant, will provide different shapes, will guarantee the shapes of the curve in the cross section, and to be able to design different type of panel based on these two approaches. They also try to increase the number of shapes which can be represented by this approach, and they also try to use the polar coordinates. So in this changing to the pattern into the polar coordinates, they can change the shapes, for example, in the initial cross section, and you can have another cross section where the shape size is different. So they use this polar coordinate to change the shapes in the cross section. But in this approach, there are several limitations, so not many shapes can be represented. Also recently, the application also of these shapes in the MIT group, they have also included for the development between these two shapes, the including of Tashimiura, but it's also this approach for the group of MIT is also based on the two curves in the developed initially by Saito and Professor Nojima. So in our approach is different, and it's based on instead of trying to design the shape, we try to use a constructive solid geometry to based on some existing shape, try to develop our approach. So for constructive shape geometry, it's just a simple approach in mathematics where you have different equations to represent some shape like cylinders, spheres, or cubes, and you can combine these shapes by using some operations like union or intersection or difference and to create some complicated shape. The representation can be different from including parametric, implicit, so different forms of representation of the shapes which can be combined. In our approach, we try to remove this representation by do two equations, and we can represent any shape. So once we have the shape, we can make some intersection with the uniform honeycomb, which is adapted to the bounding box of this shape. So from the intersection, we can receive the shape in the right side, which includes the honeycomb definition for this shape. So after that, in this group of there will be many honeycomb cells, which are the amount depends on the size of a unit cell, but almost all these shapes will be included in these 4 cases. So as it was described in the initial paper by Saito, Peregrino, and Nojima in 2014, where they say the only shape that cannot be represented in the paper is the non-convex shapes, where you have the paper will overlap due to this non-convexity in the 3D shape. So in our case, we just change this shape by including some flaps in order to separate this overlapping part into the new one. And for all these shapes, we modify the pattern, and then we try to make some approach to optimize how to combine all these small cells in order to create a pattern. So in our approach is mainly is very close to the approach used by Carlish and Griffith, where they use a recursive formula. In their case, they are based on the 2 curves in the top and the lower part, and they use an iterative approach to find the movement of each cell in order to create the pattern which keeps the longitudinal representation of the pattern instead of using some curved in that way. So they try to keep straight the pattern, the final pattern. So, but in their case, they do not focus on the optimization. I mean, the ways, the use of materials. So in our case, we try to optimize, to minimize this size in the dashed line, which may let us to make an optimal use of the materials when we try to create the final pattern. So in that way, we try to optimize the folding line and the gluing zone, this gluing zone, to manufacturing this pattern. So for this case, we propose to start with a 2-step algorithm. The 2-step algorithm just has as input the model in 3D model, any 3D model, which could be a mesh model or could be a solid model. In the case of a mesh, we included we convert the mesh to the solid one in order to be able to do the Boolean operation with the original uniform honeycomb. So we include the cell size and the direction of the cells in the model. So based on this, we calculate the bounding box and the number of cells we will have in the x direction, the y direction, and we have 2 paths. So for all the cells, firstly we calculate the maximum size and the minimum size of all of the unit cells of all these unit cells in one row, and then we update the value of the maximum size for one column in this row, and after that we can make the combination. I mean, in this step 12, we have the intersection of the model, which all these faces we have already calculated. We can calculate the points in this surface, and from this point we can make some rotation in order to receive the initial pattern. After what we have this initial pattern, we optimize the pattern based on this bounding box to assign the gluing mountain and the valley lines. So in order to show some preliminary results, we just in this case we tested the algorithm with 2 big data sets. So we have the single data sets in the left, which is has a paper. They have a lot more than 10,000 models which are optimized for 3D printing. They are mainly based on a surface mesh. So, but we converted this to solids by making it manifold and filling the space. And after that, we made we applied our algorithm. Also, for the original CAD, for the CAD models, there are also data sets called ABC, where we can find a lot of CAD models mainly for geometric deep learning. But these models, we also use it to test how much our algorithms can represent the shape in the 3D based on the Kirigami honeycomb. So we use some from this data set, some example, which is mainly the bunny model, which is included in both data sets in different shapes. And also we have for the 3D printing, and also we have some representation as a CAD CAD model. So in this CAD model, this is the size of the model, and then we can see that after we made the intersection, the Boolean operation with a uniform honeycomb, we receive the one in the lower part, which is the representation of a bunny based on the honeycomb. And then after the algorithm, we receive the pattern in the lower part. As you can see, this pattern is like a one-dimensional pattern, which you have only mountain valley line, and this can be in this case we build this by hand, and we receive the bunny model based on the honeycomb. We can see different waves to different directions of the bunny model. As it was created in the paper, we include some bar in order to keep it, and the ear in order to take the pictures. So this can be extended to many same results we receive with many of the models in the data set. So the main conclusion is that the Kirigami honeycomb has been created for complicated shapes using the combination of a computed solid geometry with an optimization approach to reduce the waste of material. So, and compared with the traditional method, which use a double cross-section, the proposed approach can use only one sheet of material, and with a continuous origami folding machine. So this is one example of the type of pattern we receive in order to create any 3D. This is an apple, but any model can be used. So on the origami folding machine is a machine we have previously developed, which only can fold patterns in a linear way. In the accordion type patterns with a Yamatani. And in this case, we are just trying to apply this the same machine to deal with the Kirigami patterns we have received in this case. That's all. I don't know if it is too fast, or we have plenty of time for any question.
Okay, thank you very much. So, じゃあ、タチさんどうぞ。
Thank you very much for your talk. So you mentioned so you are taking the intersection between two sets using a solid model, right?
Yes.
So I was thinking that the origami is more usually modeled as not solid, but like sheet. So it's more like polygonal model.
Yes.
So is it how does this work?
Yes. Once you have a shape of a polygonal model, so if it is a manifold model, you can create a solid from the mesh. So maybe I got too fast. So, but for the surface, we made a solid from the surface, and
by adding some thickness.
No, filling the space inside, or adding some thickness. So in the case of bunny, we made some. We fill the space, fill in the holes and fill the space. But in the case of, I mean, let me see if in this another case, I mean, for example, in this case, it's very thick. So it has some thickness, and from this thickness we can see the cells in this filling this thickness. So that's
I would think of thickness of the honeycomb itself.
Yes, the haze of the honeycomb. Yes, you're right.
So you assume some thickness and then you compute the Boolean operation and you unroll it.
Yes.
I see.
So that's one way. So, and as I did not say, but maybe last time it was presented, but I did not went into detail. I just sent this paper also for patent and for PNAS. And maybe I ask you, I put your name as a possible reviewer. Maybe you will just go into detail and you could help to improve the results.
Okay. So thank you.
You're welcome.
Any other questions or comments? Okay, so I have one question. You want to minimize the, how may I say, the extra or some materials, right?
Yes.
But do you have any other some criteria? For example, you want to make much more stronger or much more get thickness or something like that. Can you adapt such a different criteria?
Well, at this point we focus on the material. I mean the use of material, because as you see the pattern here is how to say, in order to keep the shapes, this part will be, I mean, this waste will be a waste of material. We increase the size, but we can also optimize the position of the cells. For example, the direction. If we change the direction of the cell, I did not show here, but if we change the direction of the cells, we can change also the amount of material will be changed. So based on the model can be represented by honeycomb, but the direction of the honeycomb cells will be different. So there are some works by Saito Sensei which they use the direction of the cell to avoid the light. I mean the light. I mean to shut out the light in some rooms. So there are, in that case, maybe we could use optimize the direction in order to minimize the amount of light. This is another possible application. So to make it stronger, and we have not focused on this direction, but maybe it will be possible, because for using metamaterials, because we want to be able to use in metamaterial, we want to fit different shapes. So if we want to fit different shapes, not only the shape fitting, we are just now focused on the face fitting, but also by changing the angle of the honeycomb, we could need more or less force in order to fit the shape. So maybe it's also interesting to think about how to optimize the forces. Thank you very much.
Thank you.